Can somebody hear?
Ask people.
Can the people on Zoom hear me? Well, if not, they.
Hello. Hello. Is it better? No worries. Can you hear me? Like, is it okay now? Yes. All right. Perfect. Sorry about that. Right. So edit words, right? So you can actually follow this time series of how many edits you have per article. And roughly we like identify three different regimes, the ones that you can see here. Like sometimes there actually is a conflict, but people very quickly kind of arrive at a stationary state. They say, okay, we agree, this is the truth. And then all of a sudden the number of edits kind of like plateaus. Okay, but there are some other types of articles that are so like controversial, so complicated that people keep fighting pretty much forever. You know, like this page is never going to reach a stationary state. It's simply going to continue having edits and edits and edits. But quite curiously, we found also an intermediate like regime in which there were kind of like small scale wars. They would get resolved, but then after a time of peace, conflict would appear again. Okay, there were these kind of never-ending cycles of peace and war. So the reason why I came here with Maxi was that, well, basically we wanted to try to find a simple model that would explain this, right? And the entire like instruction of Maxi, he just told me, make a model. and let's see how it works, right? So that's what I kind of tried to do. And the model, without going too much into the details, was basically a variation of an opinion dynamics model. Maybe some of you know it, this bounded confidence type of dynamics, in which you have different opinions, right? This Xi's and Xi of the people. And this notion of bounded confidence is that if two opinions are kind of close enough as parameterized by a certain parameter, then people are going to get even closer together. They're going to eventually agree. But if their opinions are too different, they cannot even talk to each other because you know that their opinions are too different, and they just stay with whatever they had before. So the small kind of like twist or thing that we did in here is that we added kind of a second bounded confidence dynamics, but also the interaction between the writers, the editors, and Wikipedia itself, the medium that we call here A. Okay, and we kind of reverted it a little bit. We basically said that if someone goes and reads the article and the article is very different from their opinion, they are not happy, so they will change the article. Okay, but in the complementary case, if they actually kind of agree with the article, based on this new tolerance epsilon A, then their own opinion is going to change because maybe they got convinced a little bit by something in the article itself. So we solved this model. I'm not going to go through the details, but the happy answer was that we managed to somehow at least qualitatively replicate these three different regimes that we found in the real data, but with this very simple bounded confidence model. Right, so this literally, you know, I was a young person, very impressionable, but this really like completely changed my mind, right? I thought like, this is what I want to do like forever and ever. I want to go around the world, try to find as much data about seemingly complex social dynamical processes that I can find, and then try to match or fit these relatively simple models and see if these models are going to tell us something about the system, particularly if they can be helpful in identifying mechanisms, right? These microscopic mechanisms of interaction that are driving the macroscopic dynamics of this social system, and that maybe can tell us something about how to modify the system, simply how to understand, right? And we were roughly trying to focus our attention, or we have done that during the last few years, in kind of three different types of systems. We are interested on this, you know, like this area that is known as dynamics on top of networks, in which you assume that you have a certain social connectivity pattern between individuals, and then you're thinking about processes that happen on top. Things like epidemic spreading, social contagion, things like that. But we are also interested in the dynamics of the network itself, right? How social networks actually change in time, how people are looking for new connections, how they destroy connections with people that they no longer like, this type of things. And finally, also thanks to the influence of Maxi, we are thinking of the more complicated situations or scenario in which these two things are happening at the same time. The so-called adaptive or co-evolving networks, in which the topology of the network changes. There are also dynamical processes happening on top of the network, and these two processes are kind of coupled, and things just get a little bit more complicated, but also kind of realistic. So just to try to put this a little bit more on the ground, let me tell you a little bit about one of these examples, and particularly in the case, sorry about that, yeah, it's worked, about like processes by which the networks themselves change. So a few years ago, with some of our colleagues in Alto, we were interested in this apparent contradiction that you find a little bit in the social sciences literature, that, you know, people have been analyzing a lot of like real empirical data on small scale social networks, and they're interested in this notion of homophily. Maybe some of you know it. This idea, this tendency that people tend to try to find people who are similar to them in some sense, and then they make connections, right? But something that you see by checking the literature is that people, indeed, they find that homophily is, you know, like a process that seems to help kind of homogenize networks, like, you know, separate or segregate networks by the different attributes recognized by people. But sometimes they find different structures, like social structures, something known as core periphery networks. Again, core periphery networks are slightly different from very segregated networks in the sense that one of the groups, known as the core, tends to be very well connected, but it also monopolizes the connections of the second group. Okay, the second group, known as the periphery, is not really connected to itself, but kind of connected to the core. And our question that we had in here was like, is it possible to reconcile these two things? Can we find a very simple model that arguably has exactly the same microscopic mechanisms of interaction, but that can, in a certain regime of parameters, recreate homophilic networks, and in another one, actually lead to core periphery networks? And we thought, we had this hunch that this somehow had to do with yet another mechanism that is very important in social networks, known as triadic closure. Probably many of you already know it as well. This tendency to create triangles, right? That when I'm trying to find a new connection, I'm looking for the friend of a friend, closing the triangle, and then things happen. So once more, just like in the case of the Wikipedia dynamics, we were looking for a very, very simple model with, like as few parameters as possible that would somehow implement these two mechanisms of both homophily and triadic closure to see what happens. So the idea is very simple. You have a network, right? Then you will have static attributes of the nodes. Basically, you have a single attribute that can have two values, okay? That is supposed to replicate something like your political proclivities in a binary party system, your gender, something like that. There are two colors, right? Like the red ones and the blue ones. Then the idea is that the links are going to change in time. So in each time step of the model, like a certain node randomly selected is going to, like try to create a new connection. How are you going to make a new connection? You are going to look for the friend of a friend, a second neighbor in the network, and you will try to make a connection to close the triangle, but with a probability that is proportional to the similarity between the attributes. Right? In other words, because of homophily, you are trying to connect with your second neighbor, and because of triadic closure, you are trying to close that network. And just to keep the average degree of the network constant, every time you create a new link, you cut another one at random. Okay, so cutting of links is totally random, but the creation of links is driven by both homophily and triadic closure and parameterized by these two parameters. Where do I have them? There will be a homophily matrix, right? That is telling you the probability of connecting either with your own group or with the other one. And this parameter C that tells you how much triadic closure there is in the system. That's it. I don't go to the details. You can actually write mean field dynamical equations, a set of small master equations that tell you the dynamics of two matrices, the total fraction of edges within groups, and also the probability of connecting, taking one node, connecting to another node that is either inside the group or outside of the group, right? So you can actually write master equations for those two quantities. And once we have this system of mean field equations, you can do linear stability analysis, find the fixed points, and identify the stability of the fixed points, right? So what is the main result without going into the details? That we can see as a function of this underlying microscopic parameter that is telling you how much homophily each individual is looking for while making single connections, what the effect of that is in the total homophily in the system, basically in the overall connectivity within groups as opposed to intragroups. So the big result is that there is something that we call homophily amplification. Okay? So even if you have relatively small tendency, to look and to create connections with people that are similar to you, because of triadic closure is coloring the different curves in here. Because of triadic closure, somehow triadic closure is going to constrain the set of choices that you have to make connections to those that are inside of your own group. So homophily is going to get amplified, okay? So this works a little bit like the tipping points in segregation models like the Schelling model, for example. It's really like a mechanism that is very similar to this. But kind of nicely enough, we also realize that yes, you get that fixed point, but by playing a little bit more with this parameter that regulates triadic closure, you can actually make the fixed point of homophily unstable. Okay, there is a bifurcation. There are certain cases in which that homophily fixed point becomes unstable, and you get two new solutions. And two new solutions, once you analyze them in terms of the topology of the resulting networks, they correspond to core periphery structure. There is homophily amplification, meaning one of the groups really gets very, very well connected, but somehow the other group, the unlucky one, gets disconnected to itself and only connects to the core. So the key thing, and of course we can go through the details on this if you are interested, but basically the kind of like the key message that we thought was kind of cool in here is that you can have the same model and exactly the same set of mechanisms, which is homophily plus triadic closure, and they can give rise to two radically different structures or types of systems at the macroscopic level. One that could be identified as a very segregated system. Now you can think in terms of echo chambers, for example, in online social networks, and another one which has an additional level of asymmetry, right? A group that is very well connected, another one that is not. There are some other things that you can do with this. I will not go through the details, but you can actually try to fit the parameters of the model to real data sets. And we use this in the paper in order to classify basically online social networks and social network data sets that we had as the ones that really look like segregated systems, for example, Facebook data sets, political blogs in the US and so on, and separate them from systems that looked more core periphery-like. Okay, in which one of the groups, for example, in the last FM dataset, is so much better connected than the other one. Cool. So this was just a little bit of a motivating example to the big idea or the big notion that I want to discuss with you today, which is this idea of statistical loss. Okay, and by the way, something that is very nicely written in this monograph by Eduardo Altman that just came out a year ago or something. Maybe some of you have read it. Please give it a look. It's a really, really cool paper and well, book actually. And he's trying to implement this idea, like in a way to re-vindicate all of us physicists, in the era of big data and so on, as to what is the usefulness of very simple models, right? Because we, of course, have this big limitation when we are trying to deal with very simple models, which is that unless we are very lucky, these models are never going to have a high level of predictability. They simply cannot do it, right? Like they maybe can tell us something about the qualitative behavior of the system as a function of parameters of the model. But if you want to do forecasting, if you want to do predictions, this is really not going to work. But what are they giving us actually? They're giving us some sense of understanding, right? They're giving us an idea of how certain properties of the dynamics at a microscopic level are connecting to aggregate or global properties of the system. So whatever we lose in terms of predictability, we gain in terms of perhaps scientific understanding, right? Of a set of models that are telling us a lot about the system via relatively simple mechanisms. So what I will try to talk to you today a bit is this kind of a quest that we have been having for a few years now of trying to find this statistical loss in places, at least places that have somehow to do with temporal dynamics and something to do with social group formation. So the first one has a lot to do with Zipf's law. And this, we were already just talking about this with David a while ago. Probably all of you are familiar with Zipf's law, right? Is this one of the very first examples of what a statistical law is. The idea is that you get a corpus of words, okay? So, like whatever, you get a book, the words that are spoken in a movie, whatever it is, all of the conversations that you have in Twitter, in an online social network or whatever, you get this corpus, and then what you do is you rank the words by their frequency. Okay, you put number 1 as a word that has been mentioned the most amount of times, then the second one, and so on. And then if you do something in which in the x-axis you put the rank of the word, right, for 1, 2, 3, 4, and so on. And in the y-axis you put the frequency of that word, what you will get is a power law. Okay, so here Laszlo is very happy, and he said, like, power laws are everywhere, right? So yeah, and you get a power law that is roughly or the exponent that is associated with that is roughly similar to 1. Okay, 1 over like x to the 1. So Zipf found this already quite a long time ago. People got very excited. Actually, some people even before Zipf, like Auerbach and so on. And they actually recognized something similar to this power law decay in other systems, in other so-called score rank distributions. For example, in terms of the population of cities, of word frequency, and so on and so on. There's also a very big discussion, in case you are interested, on what the actual value of this exponent is. There are generative models that give you an exponent of 1, but there are also a few variations in there, and so on. So a few years ago, with people like Carlos Herfenson, at that time still in UNAM, Laszlo in Boston, and so on, we were interested in this idea, like what else can we say, because things like the statistical law that comes from Zipf's law, in a way, is very aggregate. It's not really telling us anything about time. So now that we have so much data all around, in particular, we have information about not only how to construct these rankings, but how rankings change in time. Maybe there's something we can say in there, right? So we, put our data collectors like hats on, and we started to try to find as much, as much data that could be identified as a ranking, right? And then we changed a little bit the question. And the question was not only, you know, like, are there some regularities in these core rank distributions, but are these regularities also, you know, stable or happening across time, or is there something else going on with this, right? So, what type of data we use? Literally use everything that we could find. And this was one of the really cool things about this project, and also one of the reasons why it took so long. Like, we were writing this paper for like 4 years because it was like a lot of it was just like data pre-processing and asking for data from friends and so on. But at the end, these are all of our data sets, right? So we think we have things like social systems in which this, you know, like in which the elements of the system are scientists ranked by citations. We have, you know, like emails that have been forwarded or not. We have universities with these rankings of universities, for example, and so on. We also have languages. This is what we were talking about a little bit before, with words ranked by word frequency. We also have companies, you know, according to the ranking of the Fortune 500 list. Countries by economic complexity. We also have infrastructural systems, cities by population size, metros by the number of people that use that metro in a particular day. We have even, you know, some data sets relating to animals. For example, hyenas that are being observed by very judicious scientists, where the hierarchy is supposed to be the social hierarchies. You know, what is the top alpha hyena, which one is the second top, and so on and so on. And we also have a lot of data from sports, okay? So, you know, like chess players, tennis players, all of these things. So again, a very large range of systems, but crucially, we have information not only on what the ranking is, but what the ranking has been year by year or day by day with certain, you know, like time units that we have that are data set dependent. So what is the thing that we see? Okay, the first one, we did this type of plots, okay? So these are plots in which we have the time on the x-axis, and on the y-axis we have the ranking, okay? Normalized such that the 0 that you have here in the top is the number 1. This is the most important element in the ranking, the top one, and then it goes down to whatever the end of the ranking is. We normalize because the size of these rankings changes a lot, okay? So the Fortune 500 is going to be 500. The ranking of good universities, sometimes they stop at 100. It really depends on the ranking. Sometimes it even changes from year by year, so this is a little bit of pre-processing that you have to do there. But anyway, and then each one of the lines is the ranking that that particular element has across time, okay? So the first very intuitive thing that you see, something that perhaps everyone understands, is that if you're in the top, it's very likely that you're going to stay in the top, right? This is on the left, you have the ranking of universities. On the right, you have the most used words in English, okay? The number 1 is like D, and then tribe, dash, and so on and so on. So the top of the rankings tends to be very stable. But as soon as you go down, there is where the messiness comes up and where chaos happens. And then you start having more changes, more fluctuations in whatever the rank associated with a single element of the system is, okay? But here is where things get like a little bit more interesting. Then we added an additional kind of like classification to the system, because some of the systems like universities, the words in the English language and so on, these systems are very open in the sense that if you see the ranking from one year to the other, there are a lot of elements that either enter the system or leave the system, okay? Think, for example, of the ranking of tennis players. You don't have the same tennis players playing over and over again, right? After 10 years, 20 years, someone retires, new players come in, that system is open, okay? But there are other types of systems, and this I put here in the lower part, that are actually closed. The set of elements in the ranking tends not to change too much from one year to the other. Examples are, for example, cities in Great Britain. In here, the time scale, the total observation period is something like 100 years, I think. So in those 100 years, there have not been really new cities founded in Great Britain. Therefore, this system is closed. Something similar happens with metro stations in Mexico, right? I think here the observation period was very, very little, so a few months. So of course, in those few months, you know, there was not a war that destroyed half of the metro stations. You kind of have the same metro stations, right? So these are closed systems. So now we do the same thing as we had before. So we start seeing what is the stability of elements as a function of the ranking, and what happens. In the top, everything is stable, like before, really cool. You go down, chaos starts happening. But once you reach to the bottom of the system, stability returns. So this is cool, right? Because now we see some sort of relationship between the openness of the system and the stability of the ranking as a function of your location in the ranking. If your system is open, you're going to have some sort of decrease, like monotonic decrease of stability, okay? Because things keep getting crazier and crazier as you go down to the bottom. But like you will have a little bit more of a symmetric behavior when you have a closed system. This is quite systematic, and the way we show this was by calculating this. We call it the rank change probability. Okay, so what we did in here is that we focus on a single like rank in the ranking, say the position 25, and then we looked at two consecutive time steps, 2 years, 2 days, 2 data points, consecutive time data points in each one of our data sets, and we calculated the average probability that an element was going to change within that rank, okay? Such that if this change probability is close to 0, then that means that you always have the same element in that particular ranking. But if this rank change is very large, then you keep having changes, okay? So these two things are basically average over time that are measuring or capturing somehow the level of stability you have in the system. So you compute them, and voila, we get basically the same that I showed you before, that you have open systems in the top. This rank change probability tends to increase, okay? And it very quickly saturates actually to values that are very close to 1. So, there's pure chaos in the system. Your level of predictability of what the next rank of your element is going to be is quite low. But if you have closed systems, this goes up, but eventually it also goes down. So there's a symmetry. There's some sort of, like extra symmetry that you get that is somehow regulated or driven by this flux in the system. Cool. So this is what the data says. So just like with Wikipedia and also just like the model of social dynamics, we wanted to make a very simple model, right? What is the most simplistic, almost absurd explanation that we can find that might maybe, like recreate, at least at the macroscopic level, the type of dynamics that we see here? Okay? Actually, when I came up with this model, I was always thinking of it as a new model, because I was thinking that this was going to be the baseline that I was going to reject, right? And like 1 year later, as I will show you, like we were never able to reject this like no baseline. I mean, that is like how silly these ranking dynamics seem to be. I mean, you don't need any mechanisms, you don't need anything. You can just basically model it with random processes. So what is a model? It has basically 2 mechanisms, right? Like the first one we call it random displacement, second one random replacement. Okay, so first off, we have the ranking. So a key thing that you have to think in there is that we have the ranking from position 1 to n0, but then also, crucially, there's always like an unobserved part of the system, okay? Because many of the rankings, they always stop somewhere, like the ranking of universities stops at 100, and then there might be other universities below, but you don't really have access to that data, okay? But that will be crucial when you think about open systems, because elements kind of enter the system or not. Okay, so the model will be actually closed. We will run the model up until n, but we are going to like artificially cut the system and only consider the ranking for the first n0 positions. Okay, so the first mechanism, random displacement, is going to be very simple. We pick one element uniformly at random with probability tau, and then we move it to some other position also chosen uniformly at random. That's it. Okay, and within the same time step, the second process will be with probability nu, we replace one element, okay? We choose one position uniformly at random, like this E, and then we substitute it with an actual new element, G, that has never been in the system. Okay? Yes. 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 So you pick B uniformly at random, or the location 2, and then you pick the location 4 uniformly at random, and you do this all the time. Yes, yes, yes. Purely like there's like literally nothing in here. And then you simulate this for like a lot of time. I will not go through the details, but you can actually, find an analytical solution for this type of dynamics, because it's that simple, with a quantity that we call the displacement probability. So this is the probability that you start in rank X. Sorry, this is yeah, I didn't put it in there. So this is the probability that you start at a given rank R, and after a time t, you're going to move to position X. okay? Where R and X are uniform, normalized ranks between 0 and 1, and the time is just Monte Carlo time in a simulation, right? You do, you do all of the derivations. I don't have the details here, but basically you can see that this displacement probability can actually be separated into two components. One component behaves very much like diffusion, which makes sense because that comes from this uniform movement, right? But it's going to be a special type of diffusion because the diffusion constant is actually dependent on the rank itself. So it has this very nice logistic function of x multiplied by 1 minus x. So in other words, if you are very close to the corners, you don't get diffused that much because you have a boundary, right? You cannot go, higher than position 1. You cannot go lower than position n. So in there, diffusion is actually going to be constrained by the boundaries. But as soon as you get closer to the center, then you have more opportunity to move. So there will be a component in this displacement probability that is similar to diffusion, but also because we are choosing the places for displacement uniformly at random, you also have the possibility of making long rank changes. You can move anywhere. So the second component will be this thing that we call a Levy C, because it's a little bit like a Levy flight, although not quite. Therefore, you will have also like a constant probability of moving everywhere else. But also, because we have replacement, this probability is actually not going to be conserved. So as time advances, there's always a non-zero probability that you're going to escape the system. So this entire probability is actually going to decrease with time. So there are three things that are like, driving this the probability of displacing to a given position in the ranking. Diffusive movement that tends to be very localized, then a more long-range movement to anywhere in the ranking, and then also the probability to escape the system altogether.
Sure.
Yeah.
What is N0? What is the role of N0?
Yeah, N0 actually doesn't. So N0 is going to be, you don't need it. So yeah, how to say that? Yes, because when you derive the displacement probability, actually N0 doesn't appear because you solve it for the entire system, okay? But there were certain quantities that we wanted to define only for the first N0 elements. For example, the problem, it's totally arbitrary, and actually it is not part of this. It's an additional parameter that we fit with the data. Yes, and here, like I'm just kind of focusing only on the first N0. Yes, but this technically goes beyond because it's defined until n. But we are just looking at the N0 part because that's the one that we are going to compare with data. We can go through the details a bit later if we want.
So in random diffusion,
yes.
you get the maximum square.
The maximum is, yeah. Maybe I didn't put it in here. Maybe I could fix the notation. This is the initial R0, so that's why I put it in there. Yeah. So it's the probability that starting at an initial condition R0. Exactly. Yeah. So this is R0, and I say after a certain time delta t, what is the probability that I am in any other position x? So if you're like that probability, by definition, by construction, it's always going to be maximal at R0, and then it's going to decay. Yeah. Cool. Great. So then, yes, once more, not going through the details, but basically, since we have an analytical approximation for this displacement probability, then we can write certain properties of the dynamics that we can measure from data in terms of the parameters of this displacement probability. Some things we call like the flux of elements that are entering the system, and also this probability that an element is going to be substituted by some other element between, in a certain amount of time. And we use that basically to write the parameters of the model. Remember, there are only two parameters of the model, the tau and the nu that are in there. Yes, in terms of the properties, the macroscopic properties that we see, flux and turnover. Okay, and by doing this math, actually we find, a relationship between the two parameters, meaning that if we want to recover the values of flux and turnover that we see in the data, the values of the model of the two parameters, tau and nu, actually, they cannot be all over the two-dimensional plane, but they actually have to follow a certain relationship between them. Okay, and this is what we call, at least a bit grandiosely, like the statistical law that appears from ranking dynamics. You will have these two parameters. Once more, tau regulates a little bit how much, how you are getting displaced. You are being picked by the model and you're moving from one part of the ranking to the other. And the nu in the x-axis is actually regulating how much your element is getting replaced by new elements that enter the system, how likely it is that you are going to exit. But systems are not like all over the place in this plane. They have to have a certain combination between the two. Either you have a lot of displacement, but very little replacement, or the other way around, you have very little displacement, but a lot of replacement. And the relationship between the two seems to be once more a power law. Once you rescale these parameters, very nice. So once more, Laszlo was very happy because we found another power law. Like they seem to be everywhere. Cool. So this is where I switch gears a little bit, and I try to talk to you of another system that now it has nothing to do with ranks, but we also seem to find a little bit of evidence for something that we also want to call a statistical law. This is, again, a different group of people. And in this case, we were very much interested in what are known as communication egocentric networks. Maybe some of you have heard about this stuff. This is the idea that if you put yourself as the ego, and then you see your neighborhood in the social network, the people with whom you have contacts, then a lot of research has gone into trying to understand what is the structure of these ego networks and how do they behave in terms of communication, right? In other words, how do we choose how to share our time and how we come to communicate with all of our friends in a particular social network. So once more, there's a lot of research in sociology, in anthropology about what are the supposed mechanisms that are driving communication in these egocentric networks. And one of the ideas, or one of the main mechanisms, the ones that people like the most, is this notion of cumulative advantage. Maybe you have heard about it at some point. It's basically a fancy name for preferential attachment. The idea is that if you have already chosen someone to be your best friend, someone with whom you're communicating a lot, then in the future, you are going to be more likely also to communicate with that person. You are going to preferentially kind of like choose this person over and over and over. Therefore, most of your time, your energy, your efforts in communication are going to be, driven towards a smaller set of people, not everyone else in an. This idea of, this can also be understood as some sort of reinforcement mechanism, right? A reinforcement mechanism that is able to, for example, take a system at the global level from a state that is very homogeneous to a state that is going to be more heterogeneous, because now you're kind of focusing on a small part of the system and putting all of your efforts in there. But once you start thinking about this type of cumulative advantage mechanisms, when you think about social systems, something that is also very important is size, right? That these social systems tend not to be infinite, okay? You're not going to get a power law because of cumulative attachment or preferential, cumulative advantage or preferential attachment. These systems tend to have very thick constraints. When you talk about social dynamics, one of them are cognitive constraints, the so-called social brain hypothesis. Maybe you have heard about this idea from Dunbar that simply our brains are not big enough. So if we want to interact with a lot of people, we just, we need to select a smaller subset of people with whom to interact, otherwise our heads explode, right? So this puts kind of like a natural limit on the size of our social networks. And the other one is simply that there's not enough time, right? So like days only have 24 hours, maybe we only spend 1 or a few hours in Facebook per day and that's it. So that's a constraint, right? So whatever we do, whatever is the effect of cumulative advantage and whatever is the dynamics of reinforcement, these two are going to be heavily constrained by both our brains and the limited time that we have to put in this activity, right? So here our question was, okay, what happens when you put these two things together, right? What happens to cumulative advantage in social systems, but under the heavy limitation of these well-known cognitive and temporal constraints? So once more, we go with data. We always try to start with data and see, if that can inform our selection and our creation of the models in some way. So in here, this was about communication networks, right? So we have a typical temporal network made out of communication events. So each one of these lines is an ego, an individual that is communicating with each one of his or her friends, right? The alters, friend number 1, number 2, and so on. And then you have a temporal network. Each one of the lines is an event. This event can be a phone call, an SMS, a message in Facebook, a post in an online forum, an email, whatever, okay? An instantaneous communication event that you have with this person. Once you have that and you aggregate all of this information at the ego level, you can actually create this activity time series, okay? The cumulative amount of events, communication events that you have had with each one of these friends. So we recreate this network. Now this is an egocentric weighted network in which the weights, the number of events that you have had with each one of your alters, is increasing in time, okay? So we can create finally what we call an activity distribution, okay, which is, it gives you the fraction of alters that you have that have a given value of activity, okay, a certain amount of phone calls or whatever you have with them. Once more, just like in the case of rankings, we try to recreate this. So basically, egocentric activity distributions for many different data sets. And we have mobile phone calls, millions of users in secret countries that we cannot say the name of the countries, even though everyone knows. We have email datasets, Facebook datasets, OSNs, all of this type of stuff. And for all of them, a certain amount of egos, many events, and many, many egocentric networks, because remember, you have a single egocentric network per individual. Okay? Cool. So once you do that, and we build the activity distributions per individual, well, we can see what the shape of these distributions is. Okay? So the first thing we calculate from them is how broad the activity distributions are. So we calculate this dispersion quantity. The dispersion is basically the variance divided by the mean. Okay, so the variance of this distribution divided by the mean, that's going to be a number. If it is very large, it means that your distribution is very broad. If it's small, it means that it's like, well. And now this is the distribution of dispersion over all of the egos and all of the data sets. So the first thing you see is that, well, the dispersion in itself is also dispersed, it's also broad, so there's a lot of heterogeneity, okay? And a lot of variability in these activity distributions, in the way we distribute our time across our friends. But since we are creating these ego networks, we have explicit temporal information, right? So we can actually calculate also a preferential attachment kernel. We can calculate from the data the probability that if one of your alters has activity A, what is the probability that on the next step, you're going to get activity A plus 1? Right? We calculate it because we have everything. We have in here the time series. We know every time a new event happens. So now you have in here that as a function of A, for all of the data sets, the average probability that you are going to connect with an alter that has that activity A. And this quantity is monotonically increasing. Therefore, there is something that looks like cumulative advantage or preferential attachment. The more activity one of your friends has, the more likely it is that you're going to connect with them in the future. Okay? So these are the two things that you see from the data. Dispersions are heterogeneous. Okay? So sometimes people treat all of their friends the same, but many, many times they treat them differently and you pick someone to be your best friend. But also, there is cumulative advantage. Once you pick someone to be your best friend, they are going to preferentially be your best friend and even more of your best friend in the future. Cool. So as always, and that's the theme of the talk, let's make a very, very simple model that somehow implements these two things and replicates what we are going to see in the data, right? So a very simple model of alter selection within an egocentric network. So where is the description of the model? Very simple. We start with an ego network that has a certain degree K, and initially you have a certain activity, the same for all of the alters in your ego network, A0, okay? And then in each time step of the dynamics, I'm going to select one of the alters and create a new event such that activity goes from A0 to A0 plus 1, or from A to A plus 1, okay? But how am I going to write this connection kernel? Well, we are going to choose that shape that for some of you might be familiar. That is actually Price's model for citation dynamics. Okay, so the probability of selecting an alter that previously has activity A is going to be proportional to A, but plus a certain parameter alpha. Okay, so proportional to A plus alpha. So this gives us two very simple kind of like extreme or limiting regimes, right? If alpha goes to 0, what do we have? That's linear preferential attachment, right? We are just saying that the probability of having more activity is proportional to your own activity. Cool. Kind of like a Barabashi-Albert type of model. Price invented it first, but okay. But if alpha goes to infinity, what is the shape of that? That becomes constant, right? Now it becomes independent of activity, and therefore the selection of your ego is random. So we wanted to use this model because it's a very nice kind of continuous interpolation between random alter choice for alpha going to infinity and pure preferential attachment or cumulative advantage for alpha going to 0. Okay, that's the model, and you kind of already know what is going to be the effect on the activity distribution in each one of these extremes. So then come, yes. Yeah, that will become relevant a little bit later. So in the initial model, actually, you know, the motivation for the model is the alpha, the parameter is alpha. But yes, I'm going to introduce a bit, and it will become very important later. T here, what takes the role of time is the total number of events in the network, right? Because I can start in here, you know, at time 0, or actually at time equals to A0. I can say that that's, you know, K times A0 is the total number of events. And in each new time step, I'm adding one new event, right? So time, in a way, is like the number of events that you have. So I use that T here, and I use the inverse of alpha, and beta is going to be a new version of the parameter that is already regulating for the moment in the dynamics that you are. This will become a little bit clearer later. But think, yeah. No, it doesn't disappear. No, this is equal. So like, so the free parameter is alpha. Everything else will come from the dynamics or from the data. So A0 is just the initial connectivity of the ego network, and T is the time. Yeah, or the total amount of events, right? So the single parameter, the free parameter of the model, the one that we are going to feed to data, is alpha, or you could choose beta, which is what we are going to do a little bit later. But there's a single, like the key in there is that there's a single free parameter, which is alpha, or alternative beta. Cool. So then you do all of the maths. This is my favorite part, but we don't have time to go through the maths. But anyway, the point is that you can actually write a system of master equations for the dynamical evolution of the activity distribution, P of A, okay? The probability that, the fraction of alters that is going to have a given activity A as a function of A from 0 to infinity. You can write this set of, you know, nonlinear coupled differential equations. And always when you have that type of systems of master equations, via generating functions, you can actually write a single partial differential equation that is equivalent to the original system of master equations. If you are very lucky, that equation is going to be linear. In our case, it is, because you have like some sort of one-step process. So you only make changes from A to A plus 1. So that's a one-step type of process. Therefore, this partial differential equation is going to be linear. And once it is, then you can solve it via the method of characteristics and get an explicit expression in the model for the activity distribution. Okay. In here, I put it as a function of beta, but remember that beta is alpha. And it's also, you know, like it's in terms of time. So this equation now is telling you the shape of the distribution, you know, how you are going to distribute events across all of your alters as a function of this parameter alpha that is telling you what your tendency to randomness is. Okay, let's look at that equation a little bit clearer and to see how it looks. So you can do maths and you can check that this equation as a function of alpha is actually going to have two limits or two regimes that are very well understood. Remember that in the case when alpha was going to infinity, this corresponds to homogeneous alter selection, right? You can select any alter at random to make your connection. So you can actually show, and you can make this derivation very simply, that from this expression, you get a Poissonian distribution that scales like a Poissonian, and first the Poissonian, then you can take another limit and get a Gaussian, and that scales like a Gaussian. Okay, so you get a proper kind of random alter selection regime for alpha going to infinity. But we also had the original regime, if you remember in here, when alpha goes to 0, and you almost exclusively have preferential attachment or cumulative advantage. In that case, you can also show that the activity distribution in the model is actually going to approach a gamma distribution. And this gamma has gamma scaling, okay? Is going to behave roughly like a power law with exponent equal to -1, and or like approaching -1 as a function of alpha, and then you're going to have an exponential decay. Okay, and here is perhaps like, now you will believe why we introduce this notion of the beta. Because via beta, or beta is actually a way of visualizing what the phase diagram of this system is. Okay, so in the x-axis, in here we put the actual tunable parameter of the dynamics, which is alpha. But in the y-axis, we put the total number of events, the time the time length in which we have run the dynamics. And it turns out that the dispersion, the broadness of the activity distribution in the model after a certain amount of time, it's really driven by beta, by the combination of these two parameters, not by one of them. Okay? And this actually separates the phase diagram into two areas. In one of the regimes where alpha is, like way much larger than the average, or like the amount of events that you have in your system, in that case, your activity distribution is going to be like very homogeneous, very Poissonian. But as soon as you start decreasing either alpha or increasing t a lot, you can move to the other regime in which the activity distribution is more broad. Okay, so we understand this model very nicely, and in here, like the idea is that now we have a single parameter beta, where all of the other features or parameters in the model we can get directly from the data. So we can get k from the data, because this is the number of alters you have in the data. A0 we can calculate it from the data as well. The only movable parameter, tunable parameter, is alpha, or alternatively, it can be beta. So this transforms into a fitting method per egocentric network for beta. This is what we do. I don't go through the details, but given this, now we can take each one of the data sets, look at all of the egocentric networks that we have in each one of the data sets. That, remember, one ego network per individual, okay? And do a statistical fit of the beta value for that ego in that particular data set. For one of the data sets, this is the phase diagram that you get. So once more, x-axis is the alpha that has been fitted to each one of the individuals, and the t comes from the data itself, the total number of events that you have in there. This is a heat map or an histogram over all of the individuals, sometimes tens of thousands, 30,000 individuals in each one of the data sets. So the cool thing that you see here, once more, is, well, they are distributed. There's a certain heterogeneity of the broadness of the activity distribution, but it kind of like, concentrates around this transition line, okay? This line in here that is somewhat a little bit arbitrarily, but separating a regime in which the activity distributions are more homogeneous and one in which the distributions are more heterogeneous. So remember that we have a single beta value per individual. We can actually finally calculate the distribution of beta values for all of the egos in a single data set, and do that for all of the data sets that we have. And finally, we are in the thing that we would call a little bit the statistical law in this case. If you see the distribution of beta values for all of the individuals in a given data set, that looks pretty much the same across all data sets. So somehow the fraction of people that have either narrow activity distributions or broad distributions is the same, regardless of the social platform that you use. And this is kind of weird, right? I never remember which one is which, but if you are homogeneous, beta small, then 1 over beta is large, right? So this fraction of people are going to be very homogeneous. So they treat all of their friends the same. They have the same amount of activity with each one of their friends. But the people on the other side are going to be the ones who pick their best friend. Okay, the activity distribution is very broad because they pick one best friend and the rest they don't talk too much. But the relative abundances of those two classes of people is the same, whether you're talking about mobile calls, Facebook, emails, online social networks, and so on and so on. So we got this thing, okay, this kind of universality, generic behavior, whatever it is, and we are like, okay, can we push it even a little bit further? I mean, is it really that this number, this beta, is something like a personality trait, right? Is it like a property of the individual? So this is the last thing that we did. We go back very much to the beginning. Remember that your activity distribution was created out of this temporal network, okay? And we literally separated the timeline for each one of the users into two pieces, okay? Whatever happened in the beginning and whatever happened at the end, okay? And now we treated these two as two completely different systems, two different individuals, and calculated a beta for each one of these two pieces to see if the betas would be similar or not. So we calculate this thing in here, that we call it a relative change on the preferentiality parameter, right? On this value of beta. So what do you get? Now we have here the distribution of these changes on beta. Remember, for the same individual, we're in two different periods of time, okay? And crucially, what we put in here in the x-axis is now the Jacquard index of the sets of friends that you have in the first period and in the second period. So in other words, if your Jacquard similarity index is very large, if you are in here, that means that you have the same friends. Okay, the people with whom you were talking in the first event are basically the same. You have the same group of friends. So in that case, we would expect that the preferentiality change is small, right? Because you're talking with the same people. Of course, you're going to behave the same way. But now think about the other case, when the Jacquard index is close to 0. This means that there are actually people who changed their friends totally. In the first period, they were talking with a certain group of alters, and in the second period, for some reason, they started talking with completely different people. But look at the preferentiality, the change in beta, even for those people, it's also close to 0. So in other words, the way we distribute time across our friends, as parameterized by this quantity and under the assumptions of the model, is very similar, even if we change friends. So there's something that we have with us. There's, we kind of like carry this number with us, and we say, this is the way I'm going to distribute my time among friends. And even if my friend changes, if my best friend goes to the other side of the world and we stop talking, then I'm going to pick a new best friend, and I'm going to spend the same amount of time with them. And this seems to be something that really, is platform independent, and it applies to a relatively large fraction of people. That's it. That's all that I wanted to talk to you about. Here it's just, like a couple of food for thought type of questions, because I'm actually quite interested in trying to continue this direction. Try to see how much of these so-called statistical laws are actually there, and what is the relationship between the microscopic mechanisms that are generating these statistical laws and the macroscopic dynamics that you see. Because in some cases, for example, in the very first example that I gave you of homophily and triadic closure, you actually have this phenomena that the same mechanisms can give rise to very different macroscopic phenomena, right? Like homophily and triadic closure can give rise to segregated networks or to core peripheral networks. But in some other cases, like in the example of ranking dynamics, you actually, arguably, you have many different mechanisms, right? Because we have data from social systems, from biological systems, economics, but once you look at them at the level of ranking dynamics, you end up seeing the same thing. So why is it that this happens? Why is it that sometimes you go from, same mechanisms to different behavior, macroscopic behavior, but sometimes it's like many different mechanisms to the same macroscopic behavior? So I wonder if there is something in there that could be said in general, that we could even make like a meta model that puts all of these things together. So this is it for me. Thank you so much. We have the papers in there. You can check them out. You can talk with me. Let us know if you are interested. We have openings in the Tampere Complexity Lab. It's very cold. It's very dark, but you get to like it after a few years. So please get in touch with us. There's a new Nordic Society for Computational Social Science. I don't know if some people have heard about it. We are soon going to start marketing this a little bit more. And of course, our satellite in CCS, the usual for many years now. So thank you very much, everyone.
Well, thank you. So this is open for questions or discussion.
Your ranking model,
Yeah.
you have these two parameters, right? How do you determine it from the data?
Yes.
The next.
This is not as statistically clean as we would like. This is really like, it's not even a proper fitting. We have this equation, right? As you saw the equation for the displacement probability, where do I have it in there? The equation for the displacement probability has the parameters in there, right? Like the tau and the nu go somewhere in there. So then from the data, we calculate two things. One, we call it the flux. The flux is the fraction of elements that enter or exit the system between two consecutive times. And then we average that over the entire observation period. This is just a number between 0 and 1. I didn't go through the details, sorry about that. And the second one is this so-called turnover rate. So the turnover rate we calculated as, how do we calculate it? We calculate the cumulative, so the total number of unique elements that you have seen in the system as a function of time. So you know, and then we normalize it by the size of the ranking. So in the beginning, you start with 1 because you have seen n 0 elements. But in the second time step, maybe there are some new elements that enter, so that number increases a little bit, and then it keeps increasing. And we see that this thing is going to have a characteristic slope, and we can calculate that slope by taking the derivative. And that derivative of this openness measure, both that and the flux can be calculated in the model, and they give you these two expressions as a function of tau and nu. Okay? So the way to do fitting, super nasty fitting, just I put f and O prime from the data, and I get the two values of tau and nu that would give you those values of f and O prime. And those are the two values. So we don't have error measures, we don't have things like that. This could be done better. But if you do that, and then you rescale the parameters nicely, then you get that power law relationship between the four values of f and O prime that come from the data.
Okay.
Yeah.
And this relation is just from the data.
Yes,
You get.
exactly. Yeah. So the model is free, right? So the two are independent parameters. I could run the model for any of these values, but this particular relationship comes because of the values of the parameters, and even more, it is only valid, we have to do an extra approximation and there, and it's only valid for nu very close to 0, so for almost closed systems. Yeah, so this is an approximate like relationship, only valid for empirical data. Yeah.
Okay.
Anybody else?
So in these regimes that you discuss about the ego networks, the homogeneous or heterogeneous.
Yeah, for the
Is it-
centric communication network, right?
Yeah, is it real? I mean, yeah. I mean, I don't know. I mean, is it so there's a clear cut?
No. This is a crossover. That's why, like, we shouldn't even call this is not really a transition. This is just a crossover, at least as far as I know.
Because social networks, I would expect some I mean, more variation.
There's going to be somewhere in the middle. Yeah. So as actually I mean, you can take it anyway. You can move this direction anyway, but just by moving alpha, you are going to continuously change from something that looks like a gamma distribution to something that looks like a Poissonian distribution. Actually, even mathematically, I think this is kind of cool because I don't know if the mathematicians have a continuous interpolation between these two, like an analytical functional form for a probability distribution that continuously interpolates between a gamma and a Poissonian. Probably this is useless, but we found one, and that's quite nice. So yeah, it's continuous. This is a crossover. There's nothing like funky happening in there in the middle. And the ego network should be, as actually we see it in here, right? So the real ego networks, once you fit the model and you get an alpha or a beta for each one of the ego networks, they're just somewhere in there. And they tend to, this is one data set, and in here you see all of the other data sets. I don't know if you can see them, but the cloud, this is very qualitative, the cloud always kind of looks like an L. And I don't know why. So, but like for all of the data sets, it seems to be like an L, you know, this kind of shape. So that's, again, this is part of the information that this distribution is very, very similar across the different systems or different modes of communication. Mhm.
Thanks, Gerardo. If you can go back to the slide of the ranking that Tony was alluding to before, I also had a question there. I mean, even if the fitting might be done better, the relationship is so clear, right? So, do you have any insight of why that happens?
Yeah, this is not there yet, to be honest. Like the only thing we tried to say in the paper, and we kind of ended in here, was that the relative position of the data set across this line is going to tell you a little bit about the predictability of the ranking as a whole. Because if you go too much in this direction of replacement, the system becomes inherently less predictable. Because you are replacing elements, you are adding new elements in arbitrary positions of the ranking, so you cannot really say a lot about it. But if you move in this direction, then the system becomes a bit more predictable because it becomes slower. So things are driven by displacement, by this slow diffusion. So you can give a good guess if you were, because of this peak in here, where do we have it? Right? Because, you know, if you're somewhere in the ranking, if the movement is mostly diffusive, then in the next time step, you can say something, you can give a relatively good guess of what your ranking is going to be, right? So in a way, we are saying that if you are here, you are relatively predictable a little bit, but the more you move in this direction, we have no idea what is going on because the system is more open, there are more fluctuations, there are more things going on. So we were but why do we have actually that relationship, and why you cannot be, for example, in here or on the other side? We don't know.
I mean, the fact that they are anti-correlated somehow, it should have an explanation,
I
right?
think it should have an explanation, yes. And that would be like a very nice follow to this, because indeed, like in the model, these were just the two independent mechanisms. You can have them in any combination, but why do you have a correlation? Why, when you have displacement, you don't get replacement? Yeah, that's a good question. It would be nice to go there.
Thank you. Is there a question from the people on Zoom? I don't know. Probably not.
Yes.
Oh, yes. They are actually hyenas. So this is a data set of something like roughly 90 hyenas or so. And biologists are following them. And based on their social behavior, or how they bite each other, then they define a social hierarchy of who is the top, who is the second top, and so on. And yeah, we got it from one of the biologist friends of Carlos. Here's so it's like 300, totally 300 hyenas, 23 observations. Look at this, like every year. So they are following the same group of hyenas during 20 years. Like this is conviction in science, not like us. I get bored after 2 years. 2 decades, they follow the same group of hyenas. Every year they check the 40 top, and then we do this, several times, and then you get 300 in total. So yeah. Actually, when we were with, well, I don't have it in here, but yeah. I had a plot in which I had the results of the hyenas, and next to them I had the ones for the scientists, and I think that was not an accident. Yeah.
I think we should wrap up. So thank you again.
Thank you so much, Andrea.
Gerardo is around for a bit longer
Yes.
today and also tomorrow.
Also tomorrow.
When he's not busy with the PhD exam.
Yes. And I'm happy to talk with everyone, so just let me know.